Mr. Tarun. Okay. Everyone with earbuds is going to hate you. And me. Taylor polynomials. So we just did a section developing Taylor polynomials, which model behavior of other more complex functions. Now we're going to move into the idea of something called a power series and determining intervals of convergence on a power series. Because after you develop a Taylor polynomial, which is a partial sum of a certain number of terms in a polynomial, we're going to expand this into Taylor polynomials. But let me just kind of point something out here. P sub n of x is equal to f of c. So basically the function you want to model with a polynomial evaluated at the center of that polynomial, which will become the center of convergence when we move into Taylor series. F of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. And then we have the third derivative of f evaluated at c over 3 factorial times x minus c cubed, and so on until you get to your nth term, your general term, the nth derivative of f evaluated at c over n factorial times x minus c to the n. Does the pattern of these terms in the Taylor polynomial remind you of another function we studied? How about, let me add in an exponent of 1 and put a 1 factorial. And the reason why there's some space here after the f of c, you could envision an x minus c to the 0 power over 0 factorial. Does this expansion of the Taylor polynomial remind you of any previous function that you have studied? It's not exact. It's not one-to-one. That's why we have to have some extra complexity in the problems that we do today. What's f of c, f prime of c, f double prime of c, f triple prime of c? What are all these? What's going to be in our terms here at f, the third derivative of f of c? A number or a variable? Okay, so there's going to be some kind of a number. So all of the f of c, first derivative of f at c, second derivative of f of c, and so on, these are going to be numerical values. Of course, your denominator is showing up to be a factorial, but also that is going to be a denominator involving a number. X minus c to the 0, x minus c to the first, x minus c to the third, x minus c to the, or second, excuse me, then x minus c to the third, and so on until you get to x minus c to the n. Every single one of these terms has a factor of x minus c. And in every one of these terms, this factor of x minus c has an exponent that's increasing by 1. Does that ring a bell to any kind of series we've studied so far this chapter? P series have a fixed power. This does not have a fixed power. Your x minus c factor has a power of 0, then a power of 1, then a power of 2, and a 3. It's geometric. Okay? It's not exactly geometric, but we did study geometric series where we had a general term of, there could have been like an a or an a sub 1, an initial value, and then it's times what? Times r to the n, where n starts at 0 and goes to infinity. But there's some kind of numerical value, some kind of constant. Now, we don't have a total constant. There's an f of c, f prime of c, f double prime of c, and so on. So there's a little bit of extra complexity. But there's some kind of ratio to a power that's increasing by 1 as you expand that series. And we have some kind of factor in x minus c whose power is increasing by 1, just like you have with the geometric series. So our understanding of learning about geometric series and whether or not they converge in pre-calc is actually going to come back and play a major role at the end of chapter 9 as we go into developing Taylor Maclaurin series, beyond just the Taylor and Maclaurin polynomials. And indeed, we have learned a ratio test, right? We just did that a few days ago. And a ratio test, I said that was good for general terms that had factorials and had what? Powers. Yeah, variable exponents or powers. So in a ratio test, we would do the limit as n approaches infinity with some condition checks, of course. But ultimately, we did the limit as n approaches infinity of what? A sub n plus 1 divided by a sub n. And when did that ratio test show that a series converged? When the ratio, or when this limit was what? Yeah, less than 1. When does a geometric series, when does this series actually converge to some infinite sum? We have, S is equal to a sub 1 over 1 minus r. But for that series to converge to an infinite sum, and for us to be able to use that formula we learned in pre-calc basically, the absolute value of r had to be what? Less than 1. If I give you a list of numbers, and I've already got the whole whiteboard filled up, so I'm not going to write any more on here, but if I give you a list of numbers that form a geometric series, how would you test that it was geometric? You would what? How do you test if a list of numbers is from a geometric series? Ooh, okay, maybe I do need to write this up. Quick little example. I didn't expect silence there. 1, 2, 4, 8, 16, so on and so on. Is this geometric? Yeah, because 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16. Okay, so this is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. A sub 5 is getting divided by a sub 4. Or if you go out to the nth term, this would be, I guess this would be 1 times r times 1 times 2. What's the question? I asked you how you can tell a list of numbers is geometric, and you all were quiet. So I'm trying to remind you of that. So our general term here, a sub n, is 1 times 2 to the n, assuming that n starts at 0. And the previous term is what? 1 times 2 to the n minus 1. And how are we checking? If I do 8 divided by 4, 16 divided by 8, in general I'm doing an nth term and dividing it by a sub n minus 1. Well, in your ratio test, you're doing a sub n plus 1 divided by a sub n. Right? It needs to be, when you have a variable exponent, that lends itself to being a geometric series. And if you back divide, as long as you back divide a term by its previous term and get a ratio less than 1, then that geometric series is going to be what? Convergent. The infinite sum is going to exist. So there's a close relationship between the ratio test we just did and the condition for a geometric series to converge. And now I'm trying to make you see that the Taylor polynomials that we just created, there's a little bit of extra complexity, but there is a x minus c to the 0, x minus c to the first, to the second, to the third, to the fourth. There is a factor, there's a common factor, there's a common multiple in each of these terms whose exponent is growing by 1, just like your geometric series does. Hence, definition of a power series, which is a close cousin, arguably maybe even almost exactly the same as your geometric series. If x is a variable, so we're saying that where we had a constant as our ratio, which we haven't actually always had just a constant here. I'm going to remind you of that here in a second. If x is a variable, then an infinite series in the form of sigma starting at n going to infinity of a sub n times x to the n expands out to be a sub 0 plus a sub 1 to the x plus a sub 2 to the x squared plus a sub 3 to the x cubed, so on and so on until you get to a sub n to the a sub n times x to the n power. Now we're not going to stop at the nth term because that's a partial sum. We're talking about expanding a series. The upper limit is infinity. So a little plus dot 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 is called a power series. If the base of the variable exponent was a constant, we'd call it a geometric series. But they're practically the same thing. And you've already had power series in your homework. I'm going to remind you that again in a second. More generally, if you don't want to have a power series centered around just 0, which ultimately, when we go back into our Taylor and Maclaurin series, that would be a Maclaurin series. In more generally, an infinite series in the form of your summation where n starts at 0 and goes to infinity of a sub n times x minus c to the n is a sub n plus a sub 1 times x minus c plus a sub 2 times x minus c to the second plus dot 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 plus a sub n times x minus c to the n. You see the relationship to the Taylor polynomial here? Plus dot dot dot. That's sort of more your more general form of the power series. So your Taylor polynomial, which is going to become a Taylor series, is really basically just specific types of power series. Now going back into trying to make you realize that this isn't really all completely brand new, let me remind you of a couple of questions, or at least one question that you had back when we did your geometric series. You had a question in 9.2 when you just got introduced to this idea of convergent series, and we were looking at telescoping and geometric series. And there was a question that said, find all values of x for which the series converges. And I'm running out of room. So it'd be something like a series where you have 3x to the n power. Well, we were studying geometric series. You have a variable ratio to a power, and there's no upper limit, so this is assumed to be a series, not a partial sum. What does that 3x need to be for this series to converge? Your 3x has to be, come on, I'm trying to make you recall your information about geometric series. This isn't supposed to be tough. Yeah, your ratio, your variable ratio had to be less than 1, which means that I'm running out of room to write. Let me do this. Which means your ratio of 3x has to be less than 1, which means that the absolute value of x has to be less than 1/3. Very shortly in your homework, you're going to be calling this your radius of convergence. How far from the center, how far from x can you go and still have this ultimately a Taylor series or Maclaurin series act like another function, right? That convergence where your polynomial is basically, this is loosely worded, but your polynomial is acting like your more sophisticated function. So then you had x has to be greater than negative 1/3 and less than, x had to be greater than negative 1/3 and less than 1/3. Does that ring a bell? Yeah. Okay. This problem in 9.2 ties in with your infinite power series centered around 0. Whereas you had another homework problem just after that that said find the series, find all values for x for which the series converges, and it was this question. You have a summation where you have 4 times x minus 3 over 4 is then raised to an n power, right? So not strictly geometric, right? We didn't have a constant ratio, but we did have a ratio of base under that power that was a variable. And so this base and this power is a variable as a function of x minus 3 over 4. What is x minus 3 over 4? This is the factor that you're constantly multiplying by. What does that factor need to be for this? We were calling it a geometric series in 9.2, but now we're really basically calling it more specifically a power series. That x minus 3 over 4 has to be, the absolute value of it has to be less than 1. So in your homework in 9.2, we had the absolute value of x minus 3 over 4 has to be less than 1, which means you have x minus 3. When you multiply the 4 out of the absolute values, you have x minus 3 is less than 4. We're going to be identifying this as the center of the polynomial or the center of convergence. For this problem, C is 4. C is going to be 3. And the radius of convergence, the difference between the x and the minus, the difference between the x and the 3, that has to be less than 4. So your center of convergence will be 3 and your radius will be 4. Meaning that ultimately negative 4 has to be less than x minus 3, which has to be less than 4. Adding 3 to everything, you have negative 1 is less than x, which is less than 7. So for this power series, for this geometric series to converge, x has to be, well, actually specifically we were calling it geometric back then, and it is. We have x has to be between negative 1 and 7. Okay, and this is a geometric series. Your Taylor polynomials have a little bit more going on. There is that x minus c to the 0, then the first, then the second, then the third, then the fourth, then the nth, and beyond. Well, this is a polynomial, so that will stop. The power series will continue going. And we will be doing Taylor series here right around the corner. There's a little bit more going on. But there is that variable base in the power that's being constantly multiplied by. So what we're going to have to do to determine the convergence of a power series, not a geometric series, but a power series, is what we just did here, reviewing, reusing, redoing the work that we did in 9.2 with a little bit of an extra step. And it's down here in purple, but I'll get to that in a minute. Convergence of a power series centered at C. If the radius of convergence is 0, the radius of convergence is going to be what we get out of this ratio of basically a sub n plus 1 over a sub n. If the radius of convergence is 0, then the power series converges only at the center of the polynomial, the center of the series, almost like basically just we're looking at like a point of tangency, if you will. If the radius of convergence is infinity, then the series converges absolutely for all values of x. It doesn't matter where you are along the power series, it is going to give you, no matter what value of x you plug into the power series, there will be an existence of an infinite sum. Getting on to a little bit of similarity to what I am trying to remind you from 9.2 when we studied geometric series, there exists a real number where the radius is greater than 0. So here, when we have the absolute value of x minus 3 is less than 4, this is that real number. Okay? We have some real number that's greater than 0, and it's a finite number like 4. Such that the series converges absolutely for the absolute value of x minus c is less than the radius, and divergent for where the absolute value of x minus c is greater than the radius. Okay, that all sounds really complicated, but we're going to be doing a ratio test and making sure that a sub n plus 1 divided by a sub n is less than 1. That's step 1. When you have a close cousin to a geometric series, your series will not converge unless the ratio of every term divided by its previous term is less than 1. A geometric series doesn't converge if the ratio is not less than 1. So we're going to find that radius of convergence by doing a ratio test. And then we're going to test the endpoints. This is where the extra little bit, this is where all the material we learned in 9.2 to 9.6 comes into play. When you have a strict geometric series, once you have like that, those values of x that make the series converge, it is an open interval always. A Taylor series has got a little bit extra complexity, again, with those ever-increasing n derivatives over basically n factorial. So they're slightly more complex. So we're going to have to test the endpoints and see if those endpoints need to be included in the interval of convergence. We never had to worry about that with a strict geometric series. This ratio has to be less than 1, so x has to be greater than -1 and less than 7. This effectively is the interval of convergence for that geometric series with a variable power. Right here, that's why we studied the ratio test, the integral test, the direct comparison test, limit comparison test. All the stuff we've been learning is about this one last little step here. Okay. Got it? Kind of makes sense?
What is 3 again? Like there.
So when that day that I graphed the cosine function, and we graphed like a linear, quadratic, and a cubic function against it. Now those were like, effectively those were Taylor polynomials, so they didn't go on forever. But it basically, when you let the number of terms in a Taylor, this is where ultimately it's going to go. When you let the number of terms in a Taylor polynomial go forever, and you make that Taylor polynomial, as our example from the previous lesson, we made a polynomial for the cosine function centered around pi/3. This stuff down here is like how far to the left of pi/3 and how far to the right from the right of pi/3 can you make a Taylor series act like that cosine function. So that's where you have like basically in terms of application how you're making a polynomial act like a more complex function. Looking at the time, I hope I can get these examples done before the bell rings. If not, I'll just continue making them through my third period break. Now, we are not going to be doing in this lesson, we're not going to be taking derivatives and integrals of power series. But indeed, that's one of the main uses of being able to come up with a power series, ultimately a Taylor or Maclaurin series or polynomials, so that you can find areas under curves that are too complex to say maybe find an integral of. And I'll put a link in the description of this video that because I have made a video about taking derivatives and integrals of power series. I'm just not going to, with our AP syllabus and the time we have today, we won't have time to do that. Find the interval of convergence for this series. We have the summation where n starts at 0 and goes to infinity of 2 to the 2 times n factorial times x to the 2n power over n factorial. Every question that asks you to find an interval of convergence, every question that will ask you in this class to find an interval of convergence, you will start by just, okay, this is one of those questions where I need to do the ratio test. I need to make sure that every general term divided by its previous term, that constant ratio is less than 1. Again, to tie in with that, what you already learned with geometric series. So we're going to do that ratio test, which strictly is, even though you might start just writing the multiplication of the reciprocal, but we're going to be doing the limit as n approaches infinity of the absolute value. This is a sub n. So it's a sub n plus 1. So not 2n, but 2 times n plus 1 factorial times x not to the 2n, but to the 2 times n plus 1 over n plus 1 factorial. So that's your a sub n plus 1. Now that general term needs to be, we need to be able to divide that general term by the one just before it. So divide a sub n plus 1 by a sub n, so 2n factorial times x to the 2n power over n factorial. And ultimately, I may not include this in every line, but ultimately we're going to be making sure we're going to be forcing this ratio to be less than 1. We want this series, we want to find the values of x that makes this series converge, which means we need to make a sub n plus 1 divided by a sub n. We need to make that ratio less than 1. So we're going to have the limit as n approaches infinity of, okay, let's distribute the 2. So we have 2n plus 2 factorial times x to the 2n plus 2 over n plus 1 factorial times, we're going to multiply by the reciprocal of the denominator, so times n factorial over 2n factorial times x to the 2n. All right, after you show that multiplication of the reciprocal, there's always going to be a lot of cancellation. So we have 2n plus 2 bases of x, and we have 2n bases of x down in the denominator. So how many will cancel? Do we have more bases of x in the denominator or more bases of x in the numerator? In the numerator. We have 2n bases of x in the denominator and 2n plus another 2. So all these bases of x are going to cancel with all but 2 of the bases of x in the numerator. We've got n factorial and n plus 1 factorial. How will n plus 1 factorial and n factorial cancel? N factorial, you guys be a little bit quiet. N plus 1 factorial is n plus 1 times n factorial. So the n factorial will cancel. Thank you. And we've got 2n factorial and 2n plus 2 factorial. Well, your 2n plus 2 factorial is going to be 2n plus 2 times 2n plus 1 times 2n factorial. So what's going to cancel? Your 2n factorial. So let's see what we have left, because this is really getting cramped down here. And I'm old and I can't squat that long. So now we have the limit as n approaches infinity of, okay, what do we have left up here? We've got 2n plus 2 times 2n plus 1 over n plus 1. Thank you. I know you're trying to help me, but this time I actually wasn't forgetting it. What I'm going to do is I'm going to leave like a fraction for the n's and a fraction for the x's. Times our x squared. And that limit, again, needs to be less than or equal to 1. So now let's let n go to infinity. This is n squared basically over n. We have a polynomial in the numerator with a degree of 2 and a polynomial in the denominator with just a degree of 1. So this portion is going to go to what? 4. No. N squared over n is going to go to infinity. You have an n squared. You have a 4n squared over a 1n. This ultimately is going to go to infinity. So this is the absolute value of infinity times x squared is, and we do need this to be less than 1. Now, this is not any kind of like a form of indeterminate, by the way. Like there is a form of indeterminate which is like infinity times 0. But we're not letting x go to infinity. It's only n that we're letting go to infinity. So what's the only value of x that is going to guarantee that this inequality is less than 1? 0. So x has to be 0. This has a your radius of convergence. So therefore, your radius of convergence is 0. There basically isn't, I mean, basically there's like at the center of the power series at C is the only place where this series converges. The only value of x you can plug into this a sub n and have the series give a real infinite sum, approach a real infinite sum, is if x is 0. All right, let's do one more. Well, hopefully 2 more, but I'm going to do 2 more. You might not see it in class, but there's another special case where the interval of convergence is infinity, but I want to be able to answer this question about, like, you know, and to kind of like see what a full-blown question is going to look like. So we're going to take a look at this problem. So for our next example, again, we're finding the interval of convergence where we have the summation where n starts at 1 and goes to infinity of -1 to the n plus 1 power times x minus 3 to the n over n times 7 to the n power. So again, the question is, what is the interval of convergence? So every question that says what's the interval of convergence, you're going to do a ratio test. So we're going to be looking at the limit as n approaches infinity of a sub n plus 1. So -1 to the n plus 1. So n plus 1 is going to be n plus 2 times x minus 3 to the n plus 1 power over n plus 1 times 7 to the n plus 1. Now that's going to get divided by a sub n. So just to save some work, instead of doing a sub n plus 1 divided by a sub n, I'm going to do a sub n plus 1 multiplied by the reciprocal of a sub n. So times n times 7 to the n power over -1 to the n plus 1 times x minus 3 to the n power. Okay. All right, let's do some cancellation. How many bases of 7 do we have in our numerator? N of them. How many do we have in the denominator? One more. N plus 1 more. So 7 to the n is going to cancel out all these bases of 7 except for one of them. How many bases of x minus 3 do we have in the numerator? N plus 1. How many bases of x minus 3 do we have in the denominator? One less, just n. So we're going to let all those bases of x minus 3 in the denominator cancel with all but 1 in the numerator. How many bases of this kind of doesn't matter because the absolute values. But how many bases of -1 do we have in the denominator? N plus 1. How many do we have in the numerator? Just one more, right? This is n plus 1 bases. This is n plus 2. There's one more. So it's going to go away anyway because of the absolute values. And we are looking for this limit. We're looking for a sub n plus 1 divided by a sub n. The ratio needs to be less than 1. We're finding the values of x that are going to make this ratio less than 1. So we have the limit as n approaches infinity of the absolute value of what? We've got, I'm going to lose the -1. N over n plus 1. So our fraction for the n's. We've got a x minus 3 over 7. And that needs to be less than, again, 1. So we're letting n go to infinity. And we have n to the first over n plus 1. Or n to the first over another n to the first. What is the limit as n approaches infinity of n over n plus 1? 1. The power of the numerator and denominator are the same. So we're not going to do like L'Hopital's rule or something at this point. So now we have the absolute value of x minus 3 over 7 is less than 1. So we have the absolute value of x minus 3 is less than 7. So from this line of work, I can identify that C is equal to what? 3. and our radius of convergence is going to be equal to 7. And that means that we have a preliminary interval of convergence. -7 has to be less than x minus 3, which is less than 7. Adding 3 to everything, we have -4 is less than x, which is less than 10. This is not the interval of convergence. It's where we are at the moment. It's like the rough draft of the interval of convergence. Now we have to test the endpoints. Does this series converges for every value of x that's in between -4 and 10. But this is not a strict power series, or geometric series, excuse me. This is not a strict geometric series. You know, we didn't have geometric series that had like 2 bases with a variable exponent and another like factor of n that's constantly changing. So will -4 make this series, allow this series to converge? So this is where we're going into testing the endpoints. So let me pick a different color. So for x is equal to -4, now we're plugging these values into our original a sub n. So we have the series where we have -1 to the n plus 1 times -4 minus 3 to the n over n times 7 to the n. So we have to clean this up and identify what type of series it is. So this is going to be -7 to the n, so -1 times n plus 1 times -7 to the n power over n times 7 to the n. Okay, well, we have 2 factors of -1 here. We need to bring these together. So I'm going to pull the factor of -1 away from the 7. And we have the summation where we have -1 to the n plus 1 power times -1 to the n times 7 to the n over n times 7 to the n power. Well, 7 to the n divided by 7 to the n is what? Anything divided by itself is 1, so the base of 7 to the n power is out. When you multiply like bases, what do you do to the exponents? You add them. So what's n plus 1 plus n? 2n plus 1. So now we have the series of -1 to the 2n plus 1 over n. Okay. 2n plus 1 is what kind of answer? Odd. So -1 to any odd power is -1. So now we have the summation of -1 over n, which is a divergent harmonic series. So this original series does not converge at x equals -4. So guess what now? What do we have to do? We got to check for 10. So, and I'm out of space, and I kind of want to leave those notes up there for my next class. So I'm going to take this away, and we're going to do it again. So, and I'll pick a different color just so it's different in the video. Oh, no, I won't. So now we're going to do x is 10. Again, this is going back into the original series. So we have the summation, no upper and lower limit, so it's implied to be a series. -1 to the n plus 1 power times 10 minus 3 to the n over n to the 7 to the n power. Well, what's 10 minus 3? 7. So we have 7 to the n over 7 to the n. Bye-bye. See you later. You're 1. So now we have negative 1 to the n plus 1 over n, which is a what? Alternating harmonic series, a convergent, alternating harmonic, which probably should be capitalized, series. So what is the interval of convergence? Negative 4 to 10. Woo! Bam! Go do your homework. If this were, say, you know, some kind of, and when you expand this, you're going to get, you do realize when you expand this, you're going to get a polynomial. Because as you expand this, everything with an n is going to be a number. So it's going to be some kind of coefficient times x minus 3 to some power. This is going to be a polynomial when you expand this. So, you know, what fancy function is this polynomial tracking? I don't know. It could model a number of complex functions, but whatever functions it does model, it will model between negative 4 and 10. And for our next example, we have the series where n starts at 0 and goes to infinity of 4 times x to the n power over 2n factorial. And again, we're finding the interval of convergence. If you're asked to find that interval of convergence, you are always going to start with the ratio test. So we're going to let the limit as n goes to infinity of a sub n plus 1, so we have that 4x as our base, to a power of n plus 1 going in for n, over 2, and make sure you use these parentheses, 2 times n plus 1 factorial, times, really technically divided by a sub n plus 1 divided by a sub n, but we're showing a multiplication of the reciprocal, so times 2n factorial over 4x to the n power. And we are again looking for that ratio, the limit as n goes to infinity of a sub n plus 1 over a sub n. We want to find the values of x that make that ratio less than 1. So how many bases of 4n do we have in the 4x do we have in the denominator? N of them. And we have some bases of 4x in our numerator, and we have n plus 1 more. So 4x to the n cancels out from the denominator, leaving us with 1 base of 4x in the numerator. Now we've got the limit as n approaches infinity of 2n factorial times 4x. And now this is going to be 2 times n plus 1, or 2n plus 2. So in the denominator, we're going to have a 2n plus 2. And this is factorial, so we're going to multiply by the number that's in front of that, just previous to that, which is going to be 2n plus 1, and then multiply by the number that's just before that term, or factor, excuse me, which is going to be 2n. But now, see, we've got that 2n matching our numerator, so I'm going to stop here and say we have that 2n factorial, again, keeping we're going to be finding the values of x that make that limit less than 1. So with the expansion of that 2 times n plus 1, or that 2n plus 2 factorial, partially expanded out until we get a match of 2n factorial, that will cancel out. And we're looking at the limit as n approaches infinity of the absolute value of 1 over 2n plus 2 times 2n plus 1 times 4x over 1. That limit staying less than 1. As we let n go to infinity, one more time, we're letting n go to infinity. We're not letting x go to infinity. So 1 over infinity is going to approach 0. And we have the absolute value of 0 times 4x is less than 1. Well, no matter what you plug in for x, this is going to come out to be 0. So for all values of x, 0 is going to be less than 1. So our radius of convergence is infinity. So therefore, the interval of convergence is negative infinity to positive infinity. So again, for today's lesson, we did not do any derivatives or integrals of these series. I have an extension of this video that I made a few years ago. I'm going to put that link in the description below. But this is finding the interval of convergence for a given power series. I'm Mr. Tarrou. Bam! Go do your homework.